Okay, so let's start on part 3, which you'll notice it says part 2 on the slides, but actually that's because I prepared 3 batches of slides for 4 talks, and so I finished the first batch of slides, took 2 talks, but they're each getting shorter and shorter, so okay. So last time we talked about, for those, a few of you are new, we talked about S12, T12, U12, and V12, the provably total functions, and all these theories. So now, next I want to talk about translations from propositional logic, or sorry, from bounded arithmetic into propositional logic. And in effect, bounded arithmetic theories are like uniform versions of propositional logic. And so there's sort of a basic sort of a tripod of things that are connected here. We have bounded arithmetic theories, we've got the computational complexity of the provably total functions, and then we've got the associated propositional proof system. So this sounds like a very nice picture, but we actually have 2 associated propositional proof systems. So we've got the first order theory, like for instance S12. We've got the provably total functions. This is the computational complexity side of things. And then we've got a propositional proof system. And these things sort of form a tripod of 3 different ideas that are all coming together. They're different aspects of the same thing, in effect. So I'm going to now, actually, as it turns out, there's 2 different kinds of connections to propositional proof systems. There's the so-called Cook-style translation and the Paris-Wilkie translation. So I'll talk about both of these. The first one will be the Cook-style translations, and then we'll do the Paris-Wilkie translation. Okay. So let me talk a little bit about propositional logic first. So here we're talking about propositional logic. So variables range over true, false. We have connectives like and or and not, if then, if and only if, and so on. And but that's it. It's a very simplistic system of logic. And in particular, what's known as a Frege system is the usual, what I think of as the textbook proof system for propositional logic. We have a finite set of axiom schemes, and the only rule of inference is modus ponens. From if you've proved A and you've proved A implies B, then you can infer B. Okay. And we're interested in the complexity of the proofs, by which I mean merely the size of the proofs, the number of symbols in the proof. So the definition of proof size is the number of symbols. And then as an augmentation of Frege proofs, we have extended Frege proofs. So extended Frege proofs allow an extra kind of extension axiom, it's called, which basically is the following. Well, by showing an example here, we pick a new variable x and a formula A, which should not contain x, and we let x be an abbreviation for A, and operationally what this means is we can add as the new axiom x if and only if A. So x as a new variable, it should not have been used anywhere else in the proof yet. It should not appear in A, nor should appear in the last line of the proof, in the formula being proved. Okay? So it's a way to, the point of this, the first point of this is that it's a way of introducing, to try to reduce proof size. Proof size was defined in terms of the number of symbols in a proof, and there's 2 reasons why there could be a lot of symbols in a proof. One could be just a lot of steps in the proof, a lot of distinct lines, and the other could be that the formulas in the proof are really, really big. And you could view extension as a first way to reduce the size of formulas by looking for a formula A which was repeated many times, replacing it by the variable x, and thus not have to keep repeating the same formula over and over again. And so now the other catch is that you can iterate extension. So I can, having introduced x in this way, I can then make another formula which can use x and introduce a new variable, say y, that's equivalent to that. So I can iterate this process. And in this way you can potentially get exponentially big formulas represented by a single variable. In fact, the way to think about this is Boolean circuits, polynomial-sized Boolean circuits can be represented in this way. Please come on in, have a seat. So skipping the open question for the moment, the intuition is extended Frege proofs can reason about Boolean circuits. Frege proofs can reason about Boolean formulas. So the difference between a formula and a circuit is a formula, if you have a subformula, it can only be used once. If you need the same value again, you have to rewrite the same subformula out. A circuit can have fan out bigger than 1, and so an intermediate value can be reused multiple times without having to recompute it. Okay, I've been asking you guys what logic you know. Now let me ask what kind of complexity theory you know. How many people have heard of the distinction between Boolean circuits and Boolean formulas before? Oh, perfect. Very good. Okay, good. Okay, so the intuition then is you have a polynomial-sized extended Frege proof. By using extension variables, you can introduce any the values of gates in a polynomial-sized circuit. So you can basically reason about polynomial-sized circuits. And it's generally conjectured that Boolean circuits can be, well, much more succinct than Boolean formulas in that given a Boolean circuit, it may require an exponentially big formula to express the same property. So by analogy then, it's generally conjectured that Frege proofs may need exponential size to simulate an extended Frege proof. So what I mean by simulate, I mean I have an extended Frege proof of some formula, some tautology. Now I know that Frege systems are complete, so they prove every tautology, so there must be a Frege proof of the same tautology, but the question is there one that's about the same size as the extended Frege proof, or polynomially bounded by the size of it, or does it maybe exponentially bigger? It's generally conjectured you need exponentially bigger just because of this intuition about circuits versus formulas. But, coming back up to the top of the page, it's an open question. Yes, question?
You just mean super polynomial size when you say exponential?
Yeah.
Oh, whoops, there's something wrong here?
Yeah, because can I not take a circuit and...
Sorry, so was there error on the slide? Start one thing at a time. Is there a bug on the...
Exponential should be super polynomial?
Super, well...
in the second line.
Second. Okay.
Second line, wait, sorry, right here.
Second line.
Intuition.
Go to the second sentence.
Okay, intuition, extended Frege proofs can reason about Boolean circuits, period. Frege proofs can reason about, now here, it's generally conjectured that it can require exponential size. I think it's generally conjectured, oh, I see. No, this is right. It's generally conjectured that a formula might need to be exponentially bigger than a corresponding circuit. At least I would have conjectured that, but there's plenty of experts in the room who might say they don't conjecture that. Have I got it backwards? It's okay, it looks right to me. In other words, you have a circuit, and you may blow it up to be a formula. And see, basically, you have a circuit. You know, I've got a circuit, and then there's two subcircuits. But they can all use the same subcircuit repeatedly, right? So this subcircuit here, so things are going upward. Here's the output. This subcircuit maybe need to use multiple places, and so to write it as a formula, you'd have to repeat that subcircuit. And that happens iteratively going down, so it could be exponentially blow up there. Okay. Okay. Okay, so there was another question after that. No, okay, good. Oh, actually, I had a question for you.
It's confusing because you didn't talk about Boolean functions. So what is difficult to represent a Boolean function is not the circuits.
Oh, I see. Okay. So it's generally conjectured that the function computed by a Boolean circuit might require, when computed by a Boolean formula, an exponentially bigger Boolean formula. Yes. Okay. Right.
A lot more sense.
That makes more sense. Okay. Good. Okay. Okay. So that's Frege and extended Frege proofs. There's a whole, I guess everyone's really, how many people have seen Frege proofs before? Well, now you've seen one. Okay. So actually, here's a proof of A implies A. So this is the standard Frege proof system, which you might see in Stephen Claney's book, for instance. We've got some certain types of axioms, like A implies B implies A is an axiom. Actually, you can substitute any formula in, so like A implies some subformula implies A. That's also an axiom. It's a schematic. I can substitute any formula in, it's still an axiom. And I've got a couple uses of modus ponens, and there's our crystal clear, understandable proof of A implies A. Okay, so it's a bit of a mess, but it works okay. So this is partly here to just, in case you hadn't seen a Frege proof, but also partly to say why we would like a different proof system. So actually the sequent calculus, which I talked about earlier today, is also a great system for working in propositional logic. So basically, I've given a few of the rules, but basically sequent calculus is shown here for propositional logic. So here my axioms are things of the form A implies A, okay, which is, this is now a sequent arrow. So I'm going to distinguish, we'll see later on, between sequent arrows and if-then. But for the moment, it's a sequent arrow. So I've got a set of formulas on the left side, a set of formulas on the right side. The formulas on the left side are being ANDed together. The formulas on the right side are being ORed together. Here's a rule for the not inference. If I have gamma implies delta comma A, then not A comma gamma implies delta. So they read this as saying if every formula's gamma is true, then some formula in delta comma A is true, right? Well, from that it follows that if every formula in gamma and not A is true, then some formula in delta is true. That's easy to see. And the other type of rules work through the same. So for instance here, if every formula in gamma is true, then some formula in delta or A is true. Likewise, if every formula in gamma is true, then some formula in delta or B is true. It follows that if every formula in gamma is true, then either subformula in delta is true or A and B is true, just by simple case analysis. And there's other rules for the other connectives, which I'm not putting here on the slide, but you can do that as a homework assignment. And then there's the infamous cut rule, which is shown here, which is what we were talking about eliminating earlier. I don't want to get into too many details here, but just let you see a little bit of overview of this. And then there's the structural rules where you can just add extra formulas or reorder formulas, duplicate formulas, contract formulas. If you have any set of formulas, gamma implies delta, you can reorder them as well, as long as when viewed as a set, this is backwards. DJ? These are backwards. Gamma prime contains gamma and delta prime contains delta. Okay, that's okay, okay. All right, so questions on the sequent calculus? So these are our basic propositional systems. The sequent calculus, as we'll see later on, will be particularly nice for dealing with translations into the constant depth proof setting. But for the moment, maybe the only other observation is the sequent calculus is equivalent to Frege systems, right? If you take a Frege proof, you can convert it into a sequent calculus proof and vice versa with a polynomial blow-up in proof size. And if you add the extension axiom, which is not usually included with sequent calculus proofs, then in that case, it becomes equivalent with extended Frege proofs. Okay. Oh, I had examples here too. So here, just to see how much easier it is to prove A implies A in the sequent calculus, here's the proof. We have an axiom, A implies A, and then we do an implies right rule to bring the A over to A implies A. So I've got A if A, then A, right? There's two types of arrows here. There's the sequent arrow and there's the if-then arrow, right? You probably can't see it from the back of the room, but the if-then arrow is a little bit smaller, okay? Or that's too simple. Here's a slightly more complicated one, which I realized after I was looking at it this morning that this is not the shortest proof of A and B implies B and A, but it's a pretty good proof. Here's a proof that A and B implies B and A, and you can just see the rules as it goes there. Anyone see the shorter proof?
Can you just repeat the explanation of the first proof?
Oh, the first proof. Okay, good. Yes. So I didn't actually tell you the rules for if-then. I showed you the rules for and on the other slide, but for if-then, there's two of them, but the one we're really interested in is from the hypotheses A comma gamma arrow B comma delta, you can infer this. And okay, this arrow is I should maybe draw the sequent arrow really big. Right? Okay. Right. This is a lot of times people would write A implies B, but I didn't want to do it that way, the old-fashioned sort of hook for implies, right? So, but this is the rule for introducing the arrow on the right, okay? The if-then arrow on the right. So that's what's going on. That's the only inference there. The first line is an axiom, A arrow A sequence.
Now I see. So the arrows on the first, on the upper part and the arrows on the part below are
Oh, wait, there's two, there's these arrows on top of each other are the same.
Are the same, and this one is the other arrow.
Yes.
Yeah, so.
Good. Yeah. Good. Thank you for asking. Okay. So, so that's examples of proofs there. I could have simplified this by doing the and right above the, or the and left, sorry, the and right above the and left. It could have been made simpler, but at any rate, it doesn't matter.
Can you go back one slide?
Can I go back one slide? Yes, I can. Okay. Good. You got, okay. All right, so let's talk about the Cook translation. So Steve Cook actually did this for an equational theory PV. I'm going to talk about it for S12, but he did it for an equational theory PV for polynomial time arithmetic. And this equational theory was, he introduced a theory which had a function symbol for every polynomial time function. And he then, this actually turns out to have logical strength extremely close to S12 in a way that can be made very precise. But he did this earlier than the development of S12. And he showed the following, is if in this theory you could prove a polynomial time identity, f of x equals g of x. So it's not a polynomial identity, it's a polynomial time identity. So f and g are polynomial time functions. If you can prove something like that, from that you know that for every x, f of x equals g of x. We convert this into a family of propositional formulas denoted for n an integer, f equals g sub n. So think of n as a particular integer like 17, and there's a formula. Basically what this formula says is that when you have x of length n, the identity is valid. And so the variables in this, f equals g sub n, they're the bits x0 through xn minus 1 for the n-bit number x. And the theorem that Steve Cook had, is that if PV proves f of x equals g of x, then these formulas have polynomial size extended Frege proofs. Okay. And all these results lift to S12, and I'll describe that a little bit more on the next slide, but maybe there's room for questions here first. Okay.
So this includes any polynomial time function?
That is in the form represented in PV, so that the PV proves f equals g, right?
My question was, you say theory PV of polynomial time function. What are the terms?
Oh, the terms are, so there's a function symbol for each polynomial time function. There's axioms describing how they're defined from each other. And the terms are terms formed from polynomial time functions.
So what are the axioms that define them? What are the atomic ones?
Oh, so basically he used Cobham's recursive definition for the polynomial time functions, and for each, he followed those recursive definitions. For each use of it, he introduced a new function symbol, and then he had the defining axioms for that function symbol based on that. Okay, I guess I don't want to take that detour here, but that's basically what he did. Yeah. Does that make sense what I said, more or less? Yeah. Okay. Yes.
So earlier you said that Frege proofs kind of correspond to formulas and extended Frege to circuits.
Yes.
But now here we have extended Frege to formulas. Understand it, right?
Oh, I'm sorry. So both Frege and extended Frege are proving formulas. Okay, but extended Frege can use these extension variables, which gives it the power to reason about the values of circuits in the intermediate steps in the proof. So you can think of the intermediate steps of the proof for reasoning about circuits, but the final result is some formula is valid. Okay. Now, be a little careful here. These are formulas, so this is getting into a subtle point. In general, polynomial time formulas, they're computable by polynomial sized circuits. So to even express this as a formula, you have to have some extension going on to say that you've computed it with these circuits. So really buried inside these circuits, I'm not going to do this approach in my lectures. Buried inside this thing, though, is that f equals g is expressed in terms of, say, he used Cobham's recursive definition, but you could equivalently think of in terms of circuits computing f and circuits computing g, and you're assuming you're giving propositional variables encoding the entire computation of the circuit, and then say they're equal at the end, right? The values of the functions. So the point here is we have a proof, say PV proves this, or we'll later on do S12 proves it, And think of this as being, for all x, f of x equals g of x. It's a single statement. X is ranging over the integers. This then transforms to a family of statements, f equals g sub n for n equals 1, 2, 3, 4, ... I suppose 0 could be on there too, right? So we get a family of formulas which then have polynomial size extended Frege proofs. Okay, so let me describe this a little bit better for in the setting of S12. And in S12, the construction changes a little bit. Basically, we're saying let's take a sharply bounded formula, sigma b 0. So all quantifiers are sharply bounded. Suppose that S12 proves for all x, a of x. Then we're going to form these formulas, a bracket sub n, as polynomial size Boolean formula involving Boolean variables x0 through xn minus 1, representing the bits of some number x of length less than n. And maybe it's less than or equal to n, I don't know, whichever. And a sub n expresses that, this should probably be a less than or equal to here. So a sub n expresses that the a of x is true, for n-bit numbers x. And I'm not going to define this formally. I'm going to give you an example on the next slide because the formal definition is almost impossible to read. Okay, so, and even more impossible to say. Okay. And I guess I should say that this really does capture the full strength of the Cook translation because of the fact we can add polynomial time functions to S12. Okay. So here's the example. I'm going to take, written here at the top of the slide, I'm going to take the formula for all a less than or equal to x minus 1 is less than x. This is the wrong example. Shoot. Because that's not sharply bounded. Well, this is embarrassing. Okay. Well, let's do it. Okay. Let's assume that those. Okay. Replace x by length of x everywhere. But I'm going to leave it as length x because it's written on the slide. Okay. Sorry about this. This should really be a length. So basically, the translation is the following: a formula x equals a. What I should really, this translation is just a little, what I really should have been doing was doing a translation of, no, I wanted to leave, okay, never mind, it's just messed up. It should be length of x. A formula x equals a is written as a conjunction of the ith bit of x is equivalent to the ith bit of a. So it's just conjoin over n xi if and only if ai. Sorry for the confusion on this lengths. Formula xi less than a sub n would just be the statement ai and not x. There's some I between 0 and n minus 1, such that ai is true, xi is false, and all the higher order bits are equal. So we take the and for j equals I plus 1 to n minus 1 of xj if and only if aj. The conjunction of x less than or equal to a sub n is we just take the disjunction of the above two statements, for instance. We could do it directly. The ith bit of x minus 1 we can write out as a formula describing the ith bit of x minus 1 is like this. X sub I, the ith bit, is the formula, okay, xi if and only if the OR from j equals 0 to I minus 1 of xj. Okay, so this OR is true if there's no carry into position I, right? Sorry, no borrow out of position I. We're subtracting. So if it's all zeros, we subtract. We get a borrow. If it's not all zeros, then we don't get a borrow. So we're saying xi is if and only if there's no borrow. So if there's no borrow, xi stays the same value, and if there is a borrow, xi flips in value. A little tricky way to do it. And also we clamp. Minus means clamping at 0. 0 minus 1 is 0 because I'm dealing with a non-negative integer. So if we also make sure we clamp at 0 by putting this extra statement on the back. Okay. And then the translation, again, it should be for all in here. Should be a length of x in here. But for all a less than or equal to x, we just take the conjunction over all a's of the appropriate This is a big conjunction. We actually take the for all and write it out as an and by taking the and over each possible value of a as an actual integer. And then we substitute in, we hard code in each possible value of a becomes hard coded in with its bits are just constant 0 or 1. So a is 0, a sub i's are all false. A sub I is 1, the lower order bit's true, and all the rest of the bits are false. So a is 1, the lower order bits are the lowest order bit is 1, and the rest are all 0, and so forth. So the and is just literally changed to a conjunction. Because this is supposed to be a sharply bounded bound, the conjunction is only polynomial size. Okay. And so it becomes a polynomial formula. And I'm sorry for this confusion here. Let's see. Let me write this on the board better here. And let me do it with the length of x there also.
Why do you think the length of x? So this is a pi 0.
It's supposed to be a delta 0. It's supposed to be a sharply bounded formula.
So this is a pi b1 formula.
This is a pi b1 formula. I could just get rid of the quantifier, but I wanted to show how a quantifier turns into an and. Let me modify this a little bit. So let's take the for all x, for all a less than the length of x. See, this is just messed up on this thing there. We'll just do this way. A is less than, what is it? This same one there. A minus 1 is less than x. Okay, let's just take the translation of this. Yeah, this slide is sort of messed up. I'm sorry about that. What this should do is it should turn into the conjunction for, and here we're thinking of A is ranging from 0 to n. Remember here, n is the length of x. N is the length of x. Okay, this conjunction, and then we take the statement here that if, here we are, if n is less than length of x, I'm sorry, if a is less than x sub n, then a minus 1 is less than x. Okay. So this here, see what's happened here is a sharply bounded quantifier. We know that we're looking at x of length n, right? Or actually, I guess actually x is less than or equal to n, the way I've said it. So the point is, we know that if a is ranging of values up to length of x, it's going to be some number between 0 and n, some particular number, right? Remember, we're dealing with a fixed n. Okay. So we take the conjunction, take the for all and make it a conjunction over the possible values of a. There's only polynomially many of them. For each value of a, we then form these formulas, but we just hardwire in for each value of a the bits that go with that number. A is 0, then a is 1, then a is 2, and so forth. For each of those, we set the bits a sub I to constant values, true or false, that code that integer. And then we substitute it into the formulas of the type I've described on the screen there. Okay. Okay. Sorry I garbled that example here. Okay. So
The only mistake was just you missed the length function of everything.
yes, but it was a pretty deep conceptual mistake. Yes. Yes. I should have put the length function on there. Yes. Yeah. And I also didn't describe how to get the ith bit of length of x, which you have to do as well. But that can be defined pretty easily as well. I mean, the ith bit of, okay, let me not define it. Okay. Okay. So the idea, though, is the conjunctions, the quantifiers, the for alls and the exists are sharply bounded. So when you turn them into conjunctions and disjunctions, there's only a small number of values to consider. So you just AND them together for all the particular values. So the x is the free variables. Its bits are encoded by these free variables x sub I, but everything else is constant, right? Okay. And so in this way you get the translation. And it's clearly polynomial size when you have the sharply bounds, because the conjunctions are just polynomial size. Okay. All right, there should probably be another question here or two.
So I don't see the difference now between this and Paris-Wilkie, but maybe you should.
We'll come to that, yes. We'll come to the Paris-Wilkie translation. Yeah, was that another question back here?
So, please once again. So we obtain a polynomial length proof in case when we restrict the statement to the first n numbers. Am I right?
Yeah, so we look at, actually not the first n numbers, the numbers with the n bits.
Yes, numbers with the n bits. So, and it looks like that we just have constructed it by our hands. So, have we used some previous result to get this construction?
No, no, no. This is just built straight from nothingness, right? It's easy to build this. Well, the only thing to check is that I've glossed over the fact we have function symbols in the language. I use -1, which isn't even really a function symbol in the language, but we have these other function symbols, but they're all easy to compute their values with polynomial size formulas, the most difficult being multiplication. There are polynomial size formulas for multiplication based on carry save addition, and so that's the hardest ones to do. But the other ones are all very straightforward to do with Boolean formulas.
My question was about the other thing. So on the previous slide we had some theorem, am I right? So, and this theorem proves the existence of such kind of proofs.
Yes.
So what is true for this statement that we get this proof from this theorem, or we don't have this proof from, or we have only the existence of such proof from this theorem?
So we have, so what happens here is we form these formulas. We're not referring to the theorem at all to form these formulas. The theorem says we have polynomial size extended Frege proofs of the resulting formulas. Those polynomial size extended Frege proofs come from the S12 proof. So we're started with the, let's see, do we have the, here it is. We have an S12 proof of for all x, A of x. A of x is this sharply bounded formula. Then these tautologies have polynomial size extended Frege proofs. Okay, so that's the point is, and again, I'm not going to give the proof construction, but it's based on the witnessing lemma. You go to a free cut free proof, all the formulas have these special forms, and then you do extra work harder than the previous witnessing lemma, which I didn't do all the work for you anyway, but you actually extract from the S12 proof the polynomial size extended Frege proofs. And again, the intuition is, the witnessing theorem tells you there are polynomial time functions that witness these sequence. Polynomial time functions have polynomial size circuits. Polynomial size circuits have values that can be defined using extension polynomially many times. And so your reason, then you have to carry along with that the provability of all the right properties, and you have to show that the arguments in S12 can be transformed into arguments in the extended Frege setting. Okay, but that's the general flow of the proof. Okay. Marco.
So, like this, I think earlier you said like there's the analogy between bounded arithmetic and propositional proofs is like Turing machines and circuits, and this is where that analogy is?
Yeah, this is one of them. Yes, there's two of them. Yeah, but yes. So we're thinking of provability in one system versus provability in another. So it's like computability in the uniform setting of Turing machines versus computing in the non-uniform setting of circuits.
Because the bounded arithmetic proof is one object, but you're mapping that to a whole family. Okay.
Right. So in particular, you could think of extended Frege proofs as being non-uniform S12 proofs. Right. So S12 proofs have to exist for one reason, but you could imagine forever accidentally finding a new extended Frege proof. Right. Just like circuits could do that to you. And okay. Okay. Cook actually proved more than this. He showed, not hard to show, is that PV and S, well, he did it for PV, but let's say for S12, the consistency of extended Frege proofs can be proved in S12. So you can prove there's no extended Frege proof of the statement x and not x for some propositional variable x. Okay? And furthermore, if you have a propositional proof system G, if S12 proves the consistency of G, then the extended Frege system P simulates G. Oh, I see I left off. EF stands for extended Frege. I don't think I said that before, but this is the short way to say extended Frege. P simulates means that if you have a proof in the system G, you can find a polynomial-sized proof of the same formula in the system extended Frege, polynomial size in the size of the G proof. Okay, so you can take a proof in the system G of a particular size, and with a polynomial blow up in the proof size, get a proof of the same thing in the extended Frege system. And all that follows pretty much from this theorem. Okay. So we get this correspondence then between S12 and extended Frege systems. Okay, good. More questions here.
So this was the question was asked some before, but what is precisely the reason that it's extended Frege and not Frege in this?
Okay, so why is it extended Frege instead of Frege? So the basic idea is S12 is dealing with polynomial time functions. Polynomial time functions have polynomial-sized circuits. They're not known to have polynomial-sized formulas. So to talk about the intermediate results of a polynomial time functions used inside the S12 proof, we need polynomial-sized circuits, hence we need extension.
Right, but it's more like because of the translation itself, that of the Koban retention or something.
But that would be when you're dealing with the polynomial time symbols for the polynomial time functions, and you have to introduce some of those by extension. You only do that just for the definition. Maybe not. You don't need to. You still need to extend more for the. You need to extend a certain amount just to express f equals g, but you might still need to extend more to prove that f equals g, right? So the translation, expression f equals g bracket sub n, would already have the extension variables in that translation necessary to express f equals g, but then you may need to do further extensions in the PV setting to prove the statements. Let's.
Right, but when you do the translation, so S12 is a sequence of four first-order formula, and then you syntactically transform them into still four propositional formulas.
Yes.
So where is the extension variable?
Because the S12 proof is it's in a first-order language, and it's talking about these existential statements that are witnessed by polynomial time functions. So those polynomial time functions have to be described in the propositional setting. The only way to describe them is to bring in the circuit value. Okay. There's some generalizations which I will state very quickly just to let you know they're out there. There's quantified propositional logic as well. So here we have quantifiers like exists Q and for all Q that range over true-false values. So many of you have probably seen quantified Boolean formulas and heard it's complete for P space. You can also do a logic for quantified Boolean formulas. And here's two new sequent calculus rules for those, for the existential statements. And if you take the logic called G sub I, this propositional logic restricted to sequent calculus using only sigma capital B sub I formulas. So capital B sub I, sigma capital B means we're talking about propositional or Boolean formulas with, well, capital B sub 1 would be only existential quantifiers. Capital sigma B sub 2 would be existential Boolean quantifiers followed by universal Boolean quantifiers and so forth. GI proofs are DAG-like. That's a little unusual for the sequent calculus, but this means that you can reuse intermediate results without having to reprove them. GI star is the tree-like form of GI. And then there's a correspondence for SI2 corresponds to GI star. Another typo. TI2, flip those twos around, corresponds to GI. Okay. And so in particular, it works even for I equals 1. So for I equals 1, tree-like sequent calculus with only sigma capital B1 propositional formulas corresponds to extended Frege, corresponds to S12. The DAG-like version of the same system corresponds to T12. So I didn't want to get into the details of this. This is due to Krycek and Pudlock, and a slightly modified version was done later by Cook and Morioka. Okay. So we get a whole hierarchy of these theories as well. Again, I'm trying to stay at the I equals 1 case as much as possible. Okay.
So for quantified Boolean proofs, tree and DAG-like are supposed conjecture to be not the same, unlike
Yes, because you increase the you increase the complexity of the formulas doing this Krycek conversion from DAG-like to tree-like. Okay. Yeah. Okay.
You should swap indices for T.
Oh, is there something? Yes. This should be TI2. Yes. Good. Okay. Okay, pause, deep breath, switch topics. Next is the Paris-Wilke, if there's no more questions, of course. Next is the Paris-Wilke translation. Okay. So this is a second kind of translation. Paris-Wilke did this first in 1985 in the setting of I delta naught. Don't worry about what that means if you haven't heard of it. But it transforms TK alpha proofs. I've switched to calling it K here instead of I. So it translates proofs at one of these of hierarchy to constant depth propositional proofs. So constant depth propositional proofs means the alternations of ands and ors. So let me write that on the board here. Constant depth propositional proof equals constant alternation of ands and ors. And I guess given how many people raised their hands earlier, it's safe to just say this is AC0 is the buzzword for this in computer science, right? Okay. Okay.
So that's under formulas and arithmetic sequence?
Yes. Again, yes. Yeah, we'll still do the sequent calculus, but the formulas will all be some constant depth. And of course, a sequent calculus is just an and implies ors. It's like one extra or on top of everything, right? Okay. So now we have, however, we're working in the system with a second order variable, second order alpha here. Okay, so we're sort of switching the propositional variables xi are no longer the bits of some number. They're the values alpha of I of some second order predicate alpha. Bounded, not sharply bounded, bounded quantifiers become ands and ors, become junctions or disjunctions. The depth of the propositional formulas is approximately k. I'll get to that a little bit at the end, depending on how you count, and especially with small fan-in gates at the bottom. So the basic idea, and I'll say this a little bit more, is we're going to take this TK2 proof, and it's got formulas with k alternations of bounded first-order quantifiers in it. And we're going to take the bounded quantifiers and change them to big ands and big ors. And then those will thus become about depth k formulas. Okay. And if we're doing this in the strictly sharply, whichever it is, sharply strict, I guess it is, sigma bi setting, we'll have a good control over the alternations of quantifiers, of ands and ors. And so let's just do an example. Okay, hopefully this example has everything okay. The pigeonhole principle. I don't want to do the, and I'm going to reuse the bracket symbol. This is not the same bracket symbol as before. So I should really be putting like superscript PWs in there, but that just struck me as too much, so I left them off, right? So we have the pigeonhole principle. One of the important statements in complexity theory is the pigeonhole principle. Likewise, the weak pigeonhole principle, which just basically you can't map, in this case, A plus 1 objects injectively into A objects. I should have written that on the screen, but I didn't. So it's not the case that you have some function f mapping A plus 1 objects into, whoops, too many bracket signs. A plus 1 objects into A objects. So we're going to code, alpha is going to code the graph of f. In other words, we'll let alpha take two inputs, x and y. Alpha of x, y means f of x equals y. And the statement would be if for every x less than or equal to a, there's a y less than a, such that alpha of x, y, then, so this is saying sort of totality. For every x, there's at least one y, but x's range over up through and including a, y's up to but not including a. Then there's distinct x less than or equal to a and x prime less than x, and a y less than a, such that both alpha of x, y and alpha of x prime y. So in other words, we have here f of x equals y and f of x prime equals y, violating the injectivity. I said injectivity, but I should write it there, injectivity. So the pigeonhole principle is telling us that we can't get an injective map from a set of size a plus 1 to a set of size a. And we can write it out this way using a second order predicate in this fashion. What the translation does is it takes the for alls and changes them into ands, the exists and changes them into ors, takes alpha sub x, y and changes it into a propositional variable. A little bit confusingly, I've called it x, but x sub ij, here I and j are the old x, y values up there. I is and for I equals 0 to n. N is like the value of a. J equals 0 to n minus 1. Xij. This is basically saying for every I there is a j, such that xij holds. Then there's some I from 0 to n, I prime from 0 to I minus 1, j from 0 to n minus 1, such that both xij and xi prime j. About as straightforward a translation as you could want. Okay, so the general principles here I've got written here. First order values are set to constants. Like I set a to the number n, a constant number n, right? They're evaluated to a fixed value. So there's no Boolean variables for bits of the first objects. Instead, the Boolean variables are for the values of alpha. Okay. So this is one of the famous principles in all of complexity theory. Okay, used all over the place. And we get this kind of translation.
Is this kind of maybe like connection to, so like the complexity class PPP or something? Like
Yes, this is this. I will talk about PPP later. Perfect. So this is complete. This type of problem is complete for PPP. Although for PPP, it's stated in terms of a function. This is in terms of the PPP. You'd essentially be given f, the function. Instead, you're only given alpha here, the graph of f. So PPP would let you evaluate y as a function of x. Here we can't do that. Okay, but other than that, it's very similar, yes. Perfect.
Can you actually explain how this alpha is being used to encode the PHP?
How is alpha being used to encode PHP? I've got a, I'm trying to say there's no f mapping the first a plus 1 integers into the first a integers. And I define alpha of xy to be the statement f of x equals y. Okay, but now now what I'm saying is that the statement up there is saying that alpha is a total, so it's a relation, right, describing the graph of f. The first part is saying if alpha is a total relation, then the second part is saying it's not an injective relation. Okay. Okay. Tony.
So in regular complexity theory, you have a relativized polynomial hierarchy that relates to AC0, and this is exactly the analog of that.
Yes, okay, good. This is a great point here. We have the polynomial hierarchy relative to an oracle, right? So think of alpha, again, as an oracle, right? So we're talking about this. Okay, good.
Confuse you more or less, depending on
Okay, if it confuses you more, ignore it. If it doesn't, it was brilliant. Okay, but this is exactly how. Remember, these are exactly how these second order variables act. They act as oracles. Okay, and so.
You said the main difference between PPP and PHP is like you're given f in PPP and in PHP you're not. But isn't alpha really just f or?
Well, what alpha is f, yes, but alpha isn't giving you any polynomial time method to compute y from x. In the PPP setting, you're implicitly given a polynomial time way to compute y from x. Here we don't have that. There's an exponential search space y might come out of. Sometimes people encode the bit graph of f, which would be alpha of x comma I would be equal to the ith bit of the value of f of x. And that turns out to be equivalent to PPP. Okay, good. I've got 10 minutes. Cut me off someplace rudely, but I have 10 minutes first. Okay, so let's talk. This maybe gets a little overly technical here, this slide, but let me see. I should have cut and pasted, I should have simplified this down. I want to talk about the depth of a propositional formula, which I sort of said already. It's the maximum nesting of blocks of ands and ors, right? So think of AC0 type counting. There's a slightly modified notion of depth called sigma prime depth, which is a little more appropriate for the setting here for translations out of bounds and arithmetic. So usually depth means just the sheer alternations of ands and ors. Sigma prime depth allows us to have a bottom layer of small fan-in gates that don't count towards the depth. So I've got a circuit of size S, and I've got a topmost gate. Let's say it's an and then the next level of gates are ors. And these are, so I've got, say we end up with ands. So these are like D levels of ands and ors. And at the very bottom, I have fan-in less than log of S. And that doesn't count towards the depth. Or sometimes we call that depth D plus a half. The half meaning we've got this extra little bit on the bottom, or maybe it should be D plus epsilon or something like that, but we don't use that terminology here. So the epsilon prime depth just means we allow a bottom layer of fan-in log n gates, and we don't count those towards the depth. Okay. All right, so
you're also not counting the implicit implicit or in the sequence, right?
no, I'm not counting the implicit or in the sequent.
So
Yes.
Narrow resolution would be depth half.
Yeah, narrow resolution would be depth 1/2 or sigma prime depth 0. So I've got sequence with very small formulas that are just strictly conjunctions or disjunctions, it would be depth 0. Right, and this comes up, okay. So, okay, there was a lot on this slide, but that's what it said. So here's the point for questions. Otherwise, I'm going to press the down arrow and keep going. Yes?
Why would you want this?
Why would you want this? Because there's these pesky little sharply bounded quantifiers down at the bottom of our formulas. We want to get a tight characterization of the alternations of ands and ors from the propositional proofs that we obtained from the Paris-Wilkie translation. And the Paris-Wilkie translation's coming from formulas that have sharply bounded formulas in the very bottom. Remember, we had these strictly sharply bounded formulas.
Are you using quantifier exchange to get all of the sharply bounded quantifiers on the inside?
Right. So you pre-use, before we do the Paris-Wilkie translation, we convert all the formulas to strict sharply bounded formulas, or strictly sharply bounded formulas, whatever I call them. So the formulas have the form exists as a bounded quantifier for all as a bounded quantifier k times, and then we've got one final sharply bounded quantifier on the inside. All the other quantifiers were bounded quantifiers, and that one's going to translate to this small fan-in thing at the bottom that won't count towards the depth. Okay. Okay. And we just, okay, the rest of the definitions are pretty, I already said all this stuff, good. So an LK proof of P, it's sigma depth prime if all the formulas have sigma prime depth D, if all the formulas in P have sigma prime depth at most D. And remember, sigma prime depth is with respect to some size S, right? So if you have an extra big proof, you can have a little bit bigger fan-in at the bottom, right? And as I just answered for Marco, these things are particularly useful for translating strictly, sharply strict sigma D formulas, okay? And the definitions do essentially to Krychek from 94. Okay, other questions on this? I get the feeling this is the kind of stuff you guys are pretty familiar with. So let's see here. There we go. So the Paris-Wilkie translation is, we assume I is greater than or equal to 2. And the formula A of A comma alpha, that's a lot of A's altogether, but just watch the fonts. It's a sigma B I minus 2 of alpha formula. And TI2 proves it, right? Then there are quasi-polynomial size sequent calculus proof. I'm using LK for sequent calculus. This goes from the old Gensen's terminology, load just a calcule for the sequent calculus. There's LK proofs P sub n of the propositional translations of these formulas such that P sub n consists of sequence of size of depth, oops, extra depth here that should come out, of sigma prime depth less than or equal to I minus 2. Okay, so the proof, which I'm not going to give you, is the first part's actually pretty straightforward. You should be able to see the idea. You can translate it just by the sort of straightforward translation to depth, to sigma prime depth less than or equal to I. By I was describing, just take the sequence, take a TI2 proof, get a free proof in which every formula is sharply strict sigma bi, and do the translation I was describing. And then these proofs have various special properties, which I don't want to get into too much, but every sequence contains finitely many formulas. They're quasi-poly height, and they're tree-like. And these properties let us simplify the depth of the proof down, and we eventually end up with a proof of sigma prime depth less than or equal to I minus 2. So you can actually get the 2 lower than expected, okay, somewhat surprisingly. Okay. And so this is the idea for the Paris-Wilkie translation. Another great place for questions, and it's maybe a good place for a stop also. Give me a question or two, and then we'll run the full length. This is clear?
Is there an explanation why intuition why you get I minus 2 instead of I?
Well, proofs are a little tricky here. I haven't looked at this in a year or so. Let's see. So basically, though, is there an intuition for this? Well, what you do is you convert the proofs to have, so one intuition is because the sequence have only constantly many formulas, you can do a certain amount of the distributive law to them without doing too much to the depth. And this actually lets you reduce the depth. Okay, sorry, without doing too much to the size. This lets you reduce the depth. And then you can convert from tree-like to DAG-like and also reduce the depth. It's not an easy construction, but it's straightforward enough. Let me see. The constructions are due to Razbarov and Kryacek. Arnold and I have a paper where we redo them. There is a bit of a bug in this paper, but it's fixable for quasi-polynomial size proofs. We should actually get this. We've written it. We haven't posted the correction to this, but we should. Okay.
Okay, no other questions. So thank you very much.
All right.